I am Sandhya, EC department. Today I am going to talk about DTFT basic frequency lock loop for GNS application. Introduction. A frequency lock loop for global navigation satellite system application is described here. The core element is the discrete time Fourier transform DTFT that leads to the maximum likelihood frequency estimation and can be conveniently implemented in a software defined radio platform. The algorithm is based on the iterative evolution of DTFT in a single frequency until the incoming frequency is locked. Precise frequency estimation is one of the most stringent constraints for global navigation satellite system receivers. Only an accurate tracking of a carrier frequency and Doppler shift with a resolution within a few tens of hertz allows the current functioning of receiver, enabling reliable position velocity timing estimations. However, with the introduction of microprocessor, new techniques based on digital signal processing have been developed, especially in a communication field, in order to obtain higher precision in reduced computational load and improve robustness against noise and communication channel impairments. The FLL processed here represent a further evolution of two previous methods based on the introduction of new elements able to lead a frequency estimation very close to ML solution. Mode of signal. In GNS receiver, the FLL operations start after the acquisition algorithms have crucially estimated the Doppler frequency and the code delay of a signal in space of an acquired satellite 20. The FLL analysis can be performed by considering the SIS transmitted by the single satellite and received at the output of RF front end. This signal can be written as R of T. General description of 2DTFT technique. The method proposed in 3 of for the estimation of FT in based on the phase difference of two consecutive DFT of two different segments of received signal. The modification adopted in 2DTFT technique or based on some theoretical results here described considering the ideal case of number disturbing function and no noise. These theoretical aspects are a particular interest as they highlight the refinement procedure for proposed technique. FLL analysis in presence of noise. Implementation of fixed point algorithm. At this point, given the initial value, the iteration present in 17 can start. In practical situation, the function g of f, fx is evaluated by means of the ratio of the DTFTs of two vectors x and xl taken from the signal. The DTFT are evaluated in a single frequency point progressively updated by the algorithm. Analysis of sequence of estimated frequency. In the noise free case, it is clear that 90 of DTFT evaluated in a single point Fi allow the exact evaluation of the value g of Fi and Fx. Therefore, also Fxi is biased by the term. The use of different pairs of vectors modifies the bias. In fact, if m is delay between two subsequent pairs of vectors, the ith value of R of f becomes a stimulated system. The 2DTFT method has been implemented and tested by stimulation using the scheme shown, where the FLL input signal is firstly decimated in order to reduce the computational complexity of the algorithm and then filter it to improve the signal to noise ratio. The 2DFT scheme. Now the real FLL implements the 2DFT technique. The first search for the FFT peak is performed in a limited frequency interval equal to the size of the acquisition frequency bin. This reduces the probability of locking a false FFT peak. Outlier problem and median filter. The frequency estimated by the FLL presents some outliers that become more and more rare with the decreasing of noise. An example of a sequence of estimated frequencies where the true frequency is Fx equal to 2500 Hz and C equal to equal to 30 dB minus H to imitate the outlier effects. The FLL output has been filtered with the median filter with length LF. that is LF values and shorted other and center value effects I becomes the estimated frequencies. Stimulated results. The scheme described in section 5 has been stimulated by using the parameters reported in table 1. The value TW equal to 20 ms has been adopted because it is similar to integration time of the usual tracking loops used in a GNSS application. L was calculated with 26 with del FA equal to 365 Hz, which corresponds to the interval of 730 Hz around the first estimation of Fx, and Ts equal to 4.4 pi by 16.3676.10 into 6 Hz equal to 10.997 mu s was experimentally determined. Conclusion and future directions. The FLL scheme described in this paper is based on the evaluation of the series of DTFT in single frequency point. The DTFT has been chosen as core element of the proposed scheme since it is known that the ML frequency estimation is based on the DTFT. The computational effect of DTFT with high resolution could be prohibitive. In our proposal, this problem is solved because the DTFT computational is performed in a single frequency point and on short time intervals, and it is updated iteration by iteration until the frequency of incoming signal is locked. This method called 2DTFT is robust and take advantage of regular structure of DTFT, which can be conveniently implemented in an STR HW platform. Thank you.